Hello, good afternoon. My name is Seng. I'm a structural engineer with Stantec. I have over 7 years of experience designing highway bridges and other structures. I've worked on four different design build projects so far, three of which are highway projects right here in Texas, and the fourth one is a rail transit project in Chicago. That is the one I will be talking about today in this presentation. Here's an overview of this presentation. I will begin with a brief introduction to CTA and show you where the project is and the locations where we did the modeling. And then we'll move on to actual model, what we assume and what are the difference comparing between a rail project to a typical highway bridge project. And finally, I will conclude with a key takeaway. The structure has been built for a little over a century ago. If you can read from here, on the construction plan, it says 1896, so more than 125 years. To put it into perspective, the current bridge that we design today are expected to last like 75 years. So this structure obviously was designed pretty well. It is still being used 75 years plus half a century. So as you can imagine, a lot of maintenance has to be done to keep it functioning, and those maintenance would also cause interruption to the service. So the main motivation for this project is to improve the service and also reduce maintenance requirement. On this slide, if you look at the picture to the left on Google Maps, you can see downtown Chicago is right here. And the project is actually about 6 miles north of downtown. And looking at the sketch on the right, you can see the stretch of this project. So it starts from Belmont, go all the way to Howard. And majority of the work actually happens in this area called Lawrence to Brynmore Modernization. The reason it is called modernization, it is because the entire structure between Wilson's and Tondale will be replaced by a post-tension segmental box girder. So it would look really nice when the project is completed. And the other main portion is down here where you see a red purple bypass. So you may ask, so what does this actually mean? I'm glad you asked. So let's check it out. So looking at the red purple bypass area for existing condition, so we have the red and purple line going north to south, and we have brown line coming across from west and just turning south. So imagine at the crossroads where there's stoplight. One car has to stop for their car to go. So in this case, when the brown train comes, the red train has to stop, or vice versa. So it actually introduces a choke point to the flow of traffic. So for the proposed condition, there will be a flyover for the brown line, as you can see right here. So comparing to a highway build project, it is like building an underpass. On this sketch, you can see the existing brown line, which we actually colored as in purple. And here is the proposed bypass, where it will go over the North Mainland. And in order to accommodate this adjustment, the mainland alignment will be shifted. So all of this green area would be a new structure, and it will be a closed deck. So what is closed deck? That is actually the typical brick structure where we have either steel or concrete girder supporting the concrete slab. And for this presentation, for the modeling part, I will be cover the open deck portion, which starts from here. And right here we have actually new span, steel span, and it is support one side on a new concrete band, and the other side will be supported by existing steel span, similar to the one that you saw previously. And then between this point to West Cornelia Avenue, I'm calling this as transition span because we are actually using existing superstructure and substructure. With the shift in the track alignment, so we have to actually make some adjustment to this area. Looking at this picture, we can see both existing and proposed alignments in one place. So from here on, the existing will stay as is. And you look at this gray area that is existing, right? And consider this red dot as the center line of the existing structure. So it actually go from north to south and do a little bit of turn and continue. For proposed alignment, it starts to actually shift a little bit up, about 3.5 feet to 4 feet, depending on the track, and then it will continue. In this view, we can see the transition span where we have the existing bands stay as is, and it continue from band 6047 all the way to 6053. So between these two bands, we have alignment shift, as I mentioned previously. So the track alignment actually shift for track 1 and track 2 about 4.5 feet going west, and track 3 and track 4 actually shift about 3.5 feet. And to accommodate for the shift, we need to provide additional support because the rails cannot just simply sit on top of the tie without close support to the stringer. And in this case, we actually have to propose 3 additional stringers between the tracks. And on the west side, we have 1 new stringer, and that would be supported by a new column. Over here, this 4 column are the existing column that you saw previously on the background picture, like earlier in this presentation. And between the column, we propose to add a new cross girder so that it can support this new proposed stringer. And these are the existing stringer that I'm drawing in red. And on the west end, we also propose like another new stringer right here. So that will be supported onto a new column. Since this project is being constructed on an existing track, which is pretty much very active every day. So to minimize the interruptions to the service, it has to be constructed in different stages. So for this case, the track 3 and 4 actually start to shift to becoming track 2 and 3. And in this view, showing a similar shift previously with the tie configuration. And majority of the shift actually happened between this span. So let's look into more detail. As you can see over here, the orange is the existing stringer, and the green line is the tracks line. And going from this band 6052 to band 6053, the track actually shifts along the bigger span. So a typical span between this stringer, existing stringer, are 5 feet, and between track actually 7 feet. And this new alignment actually going into the bigger span. So in order to show whether the existing structure is adequate or not, we have to actually do a more detailed analysis. So that's when superstructure modeling in CSI come into the picture. So now it's time to start talking about the fun part of this presentation. I know you guys have been waiting for quite a bit to get to this point. So let's see. So typically for modeling the highway projects, like a typical bridge structure, it's not much different compared to the rail bridge structure. So I will just cover the main difference. Like in this case, for a rail project, of course, the track type and live load. As you already know, it will not be HL93. By now, you might have guessed I keep repeating about track type. So what is it? So track type is nothing but this wooden flanks that's actually span between the existing stringer. It supports the rail tracks, and in a typical scenario, the rail tracks actually run directly above the stringer. In that case, we don't really have to do much modeling. However, when we have the drag shift or we are designing like a new structure, so we have to actually see the actual effects by actually producing a model. And the main difference for this open deck structure to a closed deck, we don't actually have a concrete deck, so the stringer will be non-composite as compared to the closed deck structure. So in the model, instead of pulling in like a line element for each track type, we actually use a plate element for the track type. So to account for the difference in the type spacing, we have to figure out like a factor that we can apply to the element so that it will function as if they are individual elements. So in this case, to get that factor, we just simply divide 9" by that tie spacing. For example, if you have the track tie which like at side by side, so since the width is 9" if you put it side by side, 9/9, then that would be 1. So it would behave as if we have the entire floor as a wooden tie. And in a typical scenario, if it is like, for example, at spacing at 18". That would mean 9/18, you get 0.5. So that would be the reduction factor that we should apply to the member stiffness modifier. So we actually apply that to the axle, vertical shears, and also to the main moment. And for other direction, we pretty much reduce that to 0. For example, if you have a load on this tie, it would not transfer to the next tie. It would just transfer as a shear onto the support and also the moment onto the tie component itself. And also, if there are any lateral load, there will be an axial load that would be accounted in this model. So if you recall from the previous slide where I showed the stage construction with the tie layout. So from first view, you rotate 90 degrees to the second view. And in this area C, the tie are actually placed back to back. So there is no opening between the tie. And this is actually needed because it needs to support this drag shift. And right here, before that, it has a spacing of pretty much exactly 18 inch because they actually overlap between the track 3 and track 4. So where we have this spacing, we follow it as shell elements with pretty much a 6-inch thickness, but we modify the stiffness factor by 0.5 as I showed previously. And for this pink color, we modify it with a factor of 1 because it is actually placed back to back. But we have to modify other criteria to 0 so that we will get the behavior as we want it to. And for the area where there is no track tie, we just simply set the shell element to be none. So it will pretty much behave as an empty shell. And in this area, as you can see, there is a disconnect between the two tracks on the tie. So we pretty much simulate that with the shell elements, which is none. So for the trans live load, according to the technical requirements for this project, we have two different trains. One is a passenger train, and that is used for design and for normal rating per ARIMA. And for crane train, that is a higher load, so that is reserved for maximum rating per ARIMA. So on the right, it shows the typical passenger train where P is 26.5 kip and with the spacing shown. And for fatigue and deflection analysis, we use 21.4 kip. And similar to arch load, on ARIMA, there's also a longitudinal force. In this case, is similar to braking force in arch load. And also, like if the train is on, it also contributes with centrifugal force. And for impact, on arch load, we have 33% fixed, right? But for ARIMA, the impact factor is based on the span. And in addition, the main difference here is the OE, which is the rocking effect. So that only applies to the track. So what is rocking effects? As you can see on this diagrams, rocking effect is basically an additional load, like either clockwise or counterclockwise, applying to the train wheels, which is about 20% in each direction. So if it's up on the left beam, it will be downward on the right beam, create a clockwise effects. And in the model, we will have to consider both clockwise and also counterclockwise to get the maximum effects on the member. So how do we apply this? So if you recall, like in this view, we have the track 3 and track 4 shifting to track 2 and track 3. And if we just simply have one lane per track, then we will not be able to apply that rocking effect. So to do that, we actually separate each track into two separate wheel lines. In that case, we can now apply the factor as needed to simulate the rocking effects. So after applying those considerations and any other related for requirements for modeling on a typical structure, let's look at the result. So in this case, for that same span that we saw previously, you can see if we call stringer S1, S2, S3, S4, S5, and such. On this table, we can show that on the base case, where pretty much there is no modification to the existing structure, we see that the distribution factor on this stringer S5 actually increased to 1.25. So on a typical scenario, like existing condition, we would have a track running pretty much on top of the existing stringer, directly on that, right? So that means each stringer would be supported this distribution factor of 1.0. So in this case, we see a 25% increase. So our objective is to keep it below 1.0. So in order to do that, we explore a couple of different cases. Like in this case, A5, we actually add 5 additional cross diaphragms. So we have 1 in the middle and 4 more between the tracks, where we actually have the shift, if you can see it right here. And also, so for that, we actually can show that we can reduce the effects on the stringer S5, which is this stringer, from 1.25 to just 0.94. So seems like we get what we wanted, right? But we also, in order to actually stop and choose this result, we want to see if we can optimize this a little bit further. So we just simply add 1 stringer, cross diaphragm right in the middle, and let's see what it contributes to. That is what we see right here. This is the new cross diaphragm. Everything else are all existing part of this bridge. And the result is that something that we really want like to see. Actually, it is 0.96 as compared to 0.94, which is good enough that we actually meet our goal to keep it below 1. And these are all for the moment demand on the stringer. And you might wonder, so how about shears? I didn't include the tables here, but for shear, the effect, it actually increased the more than 1, let's say 1.5, 1.7, but we have adequate capacity. Like shear, we have like a capacity over demand ratio, like more than 3 even. So in that case, we are not worried about shear. We just want to make sure the moment capacity for the existing stringer is adequate. After doing the analysis, as you can see previously, the result was to add the new cross diaphragm at midspan between the stringer S4 and S5. So when we actually do the design, we also have to check the existing member as well. And when we do that, the existing member does not work. It will need additional modification, like changing from a rivet connection to a bolt connection to get additional capacity. maybe add a couple more bolts to make it work. So then we have to actually take a step back and look at this again, like, because we don't want to actually make too much adjustment to that, as this is basically for a temporary condition, just for stage construction. So then we explore the idea of what if we remove the diagonal bracing and see if the existing stringer still have enough capacity to take the load, and if we can reduce the effects on the existing diaphragm. So with that, we come up with this configuration. Basically, we just have the top and bottom chords for the new diaphragm. And with this case, we still end up with like overstress on the existing diaphragm next to that, like 1.08 or an 8% overstress. So for temporary condition, we could possibly accept that, but then we look a little bit further and find that we can actually also reduce the required load. If you remember, the passenger load was previously actual load was 26.5 kg, but per technical requirement, we can also apply some reduction factor for a temporary condition. And also, we look into other condition report. They actually use 21.4 kg, which is the fatigue load for existing structure. So we actually go back and ask CTA for a design variant if we can also use the 21.4 kg load for this temporary condition, and we get the approvals. And with that, we can actually show that the structure would actually work without adding any members. So all of this work is mainly to show that we can do nothing. To me, I think that is the best solution if we can actually prove that. And I think this is the goal that actually make everybody happy. Like the contractor, they don't have to do additional retrofit for this temporary condition. So now you might wonder, so all of this work for modeling is for nothing, right? Actually, it's not. Like, as I mentioned previously, it is the best solution that we can come up with to show that the existing structure works as it is, so no need to do extra work if it's not needed. So make it simple. And in addition to like the previous model, we can actually use that model and make some modification to use it for actual proposed condition. Like in this case, we have the new added stringer, as I mentioned a couple of slides back. So we have a new stringer between the existing track and also one new stringer on the west end, which will be supported by new columns. And these are all needed to support the shifted track. And once we have the full models built, we can then start to extract any information that we need to meet the requirements for technical requirements or for design requirements. And in this case, the technical requirement call for improvement on the serviceability. Like in this case, let's say if here are the support and there's like an open joint in between. So if when you have the train going along that, if you have this angle tilted in both directions, then as a passenger on the train, you would actually feel that, right? like rocking along the way. So we have to meet the requirement that this delta would be less than 0.005 radian. So with the model, we can just simply look at that point and see, okay, for that service load, let's say SLD1, the deflection angle would be, let's say, 0.02 on each direction, then add up to 0.004, then it would meet the requirement. And in the case that it doesn't, then we have to start see what we can do. Let's maybe increase the stiffness of the stringer or use a bigger stringer section. Then we don't have to actually do a hand count to determine that. Just change the section in the model and run it. If there's one key takeaway from this presentation, it's not the project itself or what it does to the community in Chicago, or it's not about how we apply the drag tie into the model as a plate elements, or it's not what we come up with the final conclusion on that shift stick drag or what we need to do to make sure it works. You should remember one thing, the solution, the best solution should be the simplest one, but we might need to do a little bit more work to arrive at that. So before I conclude this presentation, I'd like to give credit to some of the sources that I used to get the some of the cool graphics on CTA, like the map and such. That belong to this presentation that was done earlier this year. And also, if you want to learn more about CTA project, it's just simply as Google it or go to YouTube and search for CTA RPM. You would learn a lot more stuff from there. Interesting stuff. And also for the technical requirement stuff, I take it from this section. And to conclude, I would like to say thanks to those who actually helped me along the way in actually working through this project, like showing me how to navigate around the project size. And when I have problem with modeling, I guess one of the key person that was helping me was Hamid Omran and Anas Ahmed. They actually helped me figure out how to fix some bugs in the model. And also thanks to Jeremiah Hudson, which gave me a lot of good QC feedbacks that I applied to the model. And also thanks to the rest of the group at Stantec that encouraged me to do this presentation. It has been fun, and actually I think I learned more about the project doing this compared to just simply doing the design work. So that was good. So thanks everyone, and hopefully you have a good day for the rest of the day. All right, bye. And if you have any question or comments, feel free to send it to my email address as shown in here.